Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics. Welcome to Speaking of Reliability. This is Fred Schenkelberg.
And this is Enrico Belmonte.
Hey, Enrico, good talking to you again. It's been a little while, and I understand you've added to your family recently, so congratulations.
Yeah. We the kid number 4, so it's quite challenging right now, but we are more than happy that she came to the world.
Oh, that's good. Well, that's cool. I'm glad everybody's well, and it all. 4 kids, geez, you're outnumbered now. You know, they have a voting block if they realize it.
Yeah.
But we wanted to, I was talking to a client a couple of weeks ago, and their presenting problem was we want to make sure we're doing enough, or it wasn't phrased that way. We want to know that we're doing enough reliability testing. And this is, what do you mean? And they said, well, we want to test to make sure everything works. Okay. Do you have unlimited funds and time? And I said, no. All right. Well, let me look at this a different way. And we went off and talked about it. And then there were a bunch of stuff that I just was like, why did you design it that way? Or what are you trying to do here? Or, what's the result here? Have you seen that? Have you run into that kind of stuff?
Yeah. Especially for reactive companies. So they say they spend all the budget they have on testing, instead of preventing. Yeah. But even in testing is quite an important part of design for reliability. There are a lot of pitfalls, So especially when you try to apply accelerated lifetime testing, for most of the company, let's accelerate. Yeah, that's the motto. Yeah, let's gain speed and let's deliver results in a couple of days, reproducing like 10 years usage in a couple of days. Right, that's the best way you can do that. Yeah, and that's
it's one of the things I learned early on, and it's the best results for how long your product will last is after 25 years with being with your customer, and you have really good tracking information. Then you will know whether it works for your customer or not. And it's in their environment, it's in their use patterns, it's with the changing factors of everything in the environment that changes over that 25 years. They move to a new home, they take their washer dryer with them or whatever. And that's the best way to do it. And everything else we do adds uncertainty to the results we get. And the further away we get from the actual use conditions and real life scenarios, the more we're guessing. Now, it's educated guesses in many cases, and we can do it well, but if we're using a mock-up of a subsystem with printed parts versus real parts, and it's not exactly in the same environment, and then we accelerate it with temperature or stress or whatever, we're a long way away from what the real conditions are. And so we have to be very careful. And I think that's the biggest pitfall I've ever seen, is that we'll put it in the chamber and we'll stress it a whole lot, and then we'll claim that it's good. And I'm like, okay, what's the linkage here, guys? How do you do that?
Yeah. So I think the problem is real, So because in most of the cases you cannot, you have a limited budget, you have limited time, and you are request to accelerate the test, reducing the testing time, And the first, I think, pitfall that you encounter when doing that is, what do you expect from the test? If you just test by sake of testing, say, without asking yourself before starting the test, what is the outcome that I expect? This is an anti-scientific approach. That's amazing. Yeah.
Well, I've heard it phrased as, well, we'll just throw it in the chamber and see what happens.
And exactly. This is not scientific at all. Yeah.
No,
so yeah. But Yeah, I think I would like to discuss with you what are potential pitfalls, because when you accelerate, you need some acceleration factors.
Yeah, you really need that model or physics or chemistry, some fundamental science that says if I increase the temperature, this chemical reaction will go faster. And many in our audience will recognize the Arrhenius equation. Yet, if it has nothing to do with chemistry and you blindly apply the Arrhenius equation, y- that acceleration factor is meaningless. So
It's
it's,
meaningless, yeah. The first point you should start is the damage mechanism. Yeah, what
yeah,
kind of damage mechanism do you expect?
yeah. Is it creep or is it shear? Is it corrosion? Is it, I mean, we're talking mechanism at the molecular level. What is it that's going on that causes this thing to fail? That's what I think what you mean by damage mechanism.
Yeah, is it, as you said, corrosion? Is it aging? Is it for polymers, for example? Is it hydrolysis? Is it something
Hmm.
chemical, or is it physical aging? No, that is really important. And I'm saying that because you mentioned Arrhenius. Yeah, Arrhenius is a typical equation, so exponential equation that everybody uses for accelerating thermal aging mechanism. Yeah,
Hmm.
but I've seen a lot of colleagues that um, they combine different acceleration laws. Yeah, for example,
Yeah,
they combine Arrhenius type with inverse power law. Yeah, they combine together multiply acceleration factor that even this is even faster than just Arrhenius. So the more effort you consider, the faster the test will be, without considering that if for example, humidity or the second stressor is not playing any role, you are just making up a test, expecting damage mechanisms that won't occur in reality.
that's right. That's right. Yeah. Or I think as another pitfall of this kind of reasoning is that you apply a stress and you understand the failure mechanism and you know you can stress that one, yet you have another mechanism that has a different activation energy and it dominates the failures. So it either it shows that it fails much quicker than you thought it would. And then you don't do the failure analysis to realize it was a different phenomena happening that was brought on because of the accelerated stress that in normal conditions doesn't exist. It's very
Yeah,
rare that that secondary mechanism would occur, but because it reacts to temperature in a much more accelerated way, it appears at the end of the game. It causes the failures when the thing that you're really most interested in is shielded because this other thing fails first. And that's a more nuanced pitfall, I think. Yet it tricks so many people that you really do have to do that failure analysis afterward. Did you get what you thought you were going to get?
yeah. Yeah, I think you can pretty much solve this issue sitting together with the team and doing kind of FMEA or DLBFM analysis and discussing what are the damage mechanisms that we can expect.
Hmm.
Damage mechanisms are, with some exception, they are more or less always the same. Yeah, you have fatigue, you have creep, you have corrosion, you have aging. It might be much more complicated, but in 90% of the cases, damage mechanisms are the well-known old ones.
Right.
And so and doing so, a review together with all the other colleagues, with the subject matter expert and the colleagues knowing about the product, is the first good habit. Yeah, um, just asking the question, what is the damage mechanism that we expect? And if you agree on that, you can start thinking how to provoke it in the proper way.
Yeah.
Yeah.
Yeah. And that's, I mean, it's a subject for a whole episode, just, acceleration factors and damage mechanisms and stuff like that. Probably many, many episodes because you really have to understand it, excuse me, in detail to get it right. Now, a whole nother field of problems I've seen with reliability testing is, and you know what I'm going to say, Enrico, is sample size. You know,
Yeah.
they're going to say, well, according to our budget and everything that's happening, you get two samples. And we want you to make sure the system test shows that it works for 10 years
Yeah.
or whatever. Even if you did everything right and have good acceleration and understand the mechanisms and do all this good stuff, um, the variability in your production line or in your material set and in the design tolerancing plays a role in how long things last. And trying to get a complete Weibull distribution, for example, for some particular failure mechanism is folly when you only have two samples,
Yeah.
unless you have a really solid model from previous work and
Yeah.
testing and everything else to fall on. But yeah, going to the lab with one sample and they say, don't break it.
Yeah.
Yeah.
Yeah, you know what I do for the people attending my training, just to let them understand what is the
Hmm.
variability. I do the exercise of testing a paper clip under fatigue load. You
Right.
know,
Yeah.
so different groups, they are testing the paper clip at different angles, and then you realize what are the typical issue that you encounter when doing testing. So there
Hmm.
is one group has large variability, the other group has a smaller variability, and they you see variability by testing a component, and you realize how it is, what is the importance of that when testing. So, and that's, I think, people need to, engineers need to also to see what is the impact of variability on testing results, and therefore choosing a good or a sufficient number of samples to have a statistical significance.
Yeah. And in some industries, it's more feasible than others. And then testing isn't really a valuable outlet for you. Is simulations and modeling and so on are much better at dealing with when you just don't have samples or enough samples. And then you use the limited samples you have to verify your model, for example. But even that's risky because if you only have one sample, you don't know if it's the first percentile to fail or the 99th percentile to fail.
Yeah.
You just don't know. And it can mislead you very quickly as to what's going on.
Yeah.
So what other pitfalls are? There's sample size, there's acceleration type stuff.
Yeah, I mean, one point is the acceleration factor. So there are, if you are a reliability engineer, and if people are listening to us, they definitely know it. You are asked for acceleration factor.
Yeah.
Hey, I need the acceleration factor for this damage mechanism. Do you have it, or should I look at it and look for it in the literature?
Right.
This is a pretty risky procedure.
Yeah.
Because you cannot apply the same acceleration factor for different suppliers, for example. Yeah, if you have like LED, what do you apply the same acceleration factor for different suppliers?
Have different
You are,
chemistry and yeah,
yeah, you
different.
are
Yep.
you are basically, you are hiding the difference between different supplier. Yeah, that's one
Right.
point. And the second point, you can make up the equivalent testing time by guessing the the acceleration factor. Yeah, and that's really, really risky. Therefore,
It,
of course, you can take a conservative assumption if you don't have the data, but on the long term, as reliability engineer, you have the responsibility to collect data also from the supplier or for the component supplier in order
mhm.
to get the degradation course.
Yeah. Yeah.
Yeah.
We have a lot of tools to where you don't need the acceleration factor. You can let the data tell you. Go use 3 different stress levels, for example, and derive it yourself. And even in that, the regression of that kind of stuff and predicting, forecasting what's going to fail in 5, 10 years that's beyond your data set, for example. We do
Yeah.
that all the time. And I remember in statistics classes, using the normal distribution and more of the quality control type stuff, it was never extrapolate beyond your data. And we do it routinely. So the,
Yeah.
the the model that we build and that activation energy or acceleration factor model and stuff like that, even a small variation in getting it wrong can be multiplied by when you try to say, well, this is good for 20 years or not. It'll be plus or minus 10 years at that point.
Yeah.
Whereas because so doubly important to make sure that you get it right. You get the modeling right, you do the testing to confirm the models are right and so on. But just pulling one out of a book and saying, oh, I'll use that, it's good.
Yeah.
There's a equation out there. I'm drawing a blank on the name of it, but it has temperature and humidity. And originally it was used for the encapsulated electronics.
Yeah, rainy spec, you mean? A rainy spec, or you need
Um,
the
I think it
Hallberg
was,
model?
yeah,
Hallberg?
Peck Hallberg had, and it was
Yeah.
basically a look at a whole bunch of testing that was done in, data, and then they just kind of fit a line to all these various other tests and said, hey, this equation kind of explains all this stuff. And it was all on epoxy covered
Yeah.
circuit, components, ICs, basically chips, to make sure it's sealed. Yet I've seen that equation used for solar panels, for delamination. I've seen it used on motors for rotor wear. I've seen it
Yeah.
used on all kinds of things that have absolutely nothing to do with where that
Yeah.
equation came from. And like, what are you doing to make sure that that equation fits? They were just trusting that, oh, this model works. And
Exactly. Yeah. That's because this equation has two parameters: the Hallberg pack, one for the inverse power law for humidity, and one for the activation energy for the exponential part.
right,
You
right.
multiply them as for the adding the acceleration factor, so you multiply the two acceleration factor, and that's all. But this is really, really risky, I see. Yeah.
Yeah.
And therefore, to my opinion, over a long time, engineers should collect data in order to get good degradation curve, because you touch another important point. So how much can we extrapolate from
Mm-hmm.
degradation curve? Because generally we exceed the threshold limit after, for example, for LED after 20,000 hours. That's something too big to be tested. Yeah.
Right.
But yeah, I think one good pragmatic approach, because people that are listening to us, they say, okay, that's everything is nice in the academic world, but I need to answer some question that my boss is asking,
Or
answering some
we should
question
be
from.
asking
Yeah.
ourselves too.
Yeah. So yeah. So when you apply this accelerated lifetime testing, yeah, starting with conservative assumption and looking and comparing then what is the expected lifetime to failure with respect to the expected service time in the field.
Mm-hmm. Mm-hmm.
This give you, okay, uh, uh, a feeling about, yeah, how much focus you need to spend to this analysis, because if you have like order of magnitude between the equivalent testing time and the expected time, service time in field, then you can say, okay, I have taken this kind of assumption. These are conservative, I know, but despite conservative assumption, I don't see any reliability problem. You can move to the next topic. That's, I think, is a pragmatic way to approach. Otherwise, the effort explodes, for engineers. Yeah.
Yeah, and it's one of those that it's you have to really think it through. Just being conservative without understanding what you're being conservative about it. I mean, you can be so
Yeah.
conservative that you actually apply very little or no stress to the failure mechanisms that are going to cause early failures, and you don't see them because you didn't even measure them or look for them, or it's that group I famously said, oh, they just threw it in the chamber and see what happens. And it
Yeah.
wasn't plugged in, and it wasn't running, it wasn't monitored. And they ended up with all kinds of problems that they could have detected if they would have had it powered up and running a self test or some sort. But they didn't. They said, no, 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 we don't have time for that. We'll just throw it in the chamber.
Exactly. Yeah.
And okay, well, it's going to get warm. And it wasn't even all that
Yeah.
warm. And you're like, all right, this is
I think the message is
worthless.
clear. Huh?
Yeah.
Yeah, the message is clear. We need to focus on understanding the damage mechanism. First, the product, and then the damage mechanism that might occur. And with this prerequisite, we can say, now let's assume a conservative approach.
Right.
That's, I think, is a good practical message we can convey today. Yeah. And of course, for some specific damage mechanisms where we are close, say, to the boundary, we need to spend more time. We need to spend more resources. But in a complex product, there might be hundreds of different damage mechanisms, and we should also be able, as engineer, to focus on the right one.
That's right. Yeah, and that's where the work comes in, the thinking comes in. One more quick pitfall is that there's a healthy amount of just basic statistics of fitting data to a curve to data, fitting a curve to data.
Yeah.
And one of the pitfalls I've run into way too many times is the people in charge of doing that analysis just open up the software, run every option they have and see which answer they like the most and use that. And
Yeah.
no. Which one actually represents your data? What distribution do you expect because of the failure mechanisms? Those you need to think through rather than blindly drawing lines until you get one you like. And it's a little bit of knowledge about regression analysis and how do you actually fit data and what is a good fit and how do you test it? How do you check your assumptions? All of those things a good statistician will do. And by comparison, a good reliability engineer that usually is doing this kind of analysis has to do because,
Yeah.
like we said, it's a small error in that fit will really ruin your day of making a meaningful estimate of future life. But don't shy away from the statistics. You got to double down on it and understand it. It's not Weibull everything because
No, no,
Weibull is pretty
definitely not. Yeah.
useful in a lot of cases, yet there are plenty of cases where it is the wrong distribution to use.
Yeah.
And so you got to really pay attention to what works and what doesn't work and does this make sense and all those other factors. Don't shy away. That's the pitfall I see is that we don't have time for the statistics. It passed the test so that we're good.
Yeah, exactly. We open a different chapter here, how to analyze, how to pick the right statistical distribution. There is a long story about exponential distribution. We
Yep.
already know there is an overuse of Weibull everywhere.
Yep.
And the point I see is that generally people assume the distribution. As they assume the distribution, they get a couple of data and then they assume, for example, log normal distribution because it's like that.
Right. And
Or
they draw a line
literature
and they're
suggests
done.
that. Yeah. But as you said, picking the wrong distribution might really affect your data, and then at the end, your decisions. So even in this case, I think we have the topic for the next.
Oh, we've got plenty of them here. And we should ask our listeners too.
Yeah.
What have you run into as pitfalls for this? And, I know one is your boss doesn't believe your results. And that's another pitfall. It's like you should check in with them. Here's the analysis, here's what I did. But the idea is there's plenty of ways we can go wrong and reliability testing, and whether it's environmental or accelerated or just halt anything that we do, we're trying to get meaningful information out of it to make decisions. And that's a good way to wrap it up, Enrico, is that it's focus on that decision, the failure mechanism, and think through the whole process. You can avoid many of these pitfalls, but there may be other ones out there, right? So if you're listening to this and thinking, oh, you missed this one, or I saw this the other day, let us know. We'd love to add to the awareness for everybody on our show. But also, we try to help you if you have a roadblock or a trouble spot or something like that. We certainly can help you out a little bit and give you some ideas and pointers to what to do and then make another show out of it, another episode out of it. You head over to accendoreliability.com/go/SOR. You can find a couple of ways to get in touch with us. Enrico and I and the other hosts of the show are available through LinkedIn and our About pages. And as we say at the end of every show, we enjoy a great deal hearing from you and what kind of questions or comments you have. And we'd love to have you join us, in the conversation by participating and giving us what you think. And that would be awesome. But anyway, good idea for a topic there, Enrico. I know that lots of us have run into a lot of these barriers at one point or another and had to figure out how to get through these pitfalls. Hopefully we don't discover them the hard way. That's why we talk about it.
Thank you, Fred, for the discussion. I appreciate it.
Yeah, thanks, Enrico. We'll talk to you soon. Take care.
Bye.
Bye-bye. Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.